14 billion years back, everything you've ever known erupted from a space tinier than a grain of sand. But hold on, we're about to dive into something that'll shatter your understanding of reality itself. We're going beyond that moment, into a realm where clocks never ticked, where emptiness wasn't even empty, and where asking what happened before makes about as much sense as asking what's south of the South Pole. You ready for this? Because once we cross this line, there's no going back to seeing the universe the way you did 5 minutes ago. Let's begin. Part 1. The border of time and existence before the Big Bang. The TO moment and the absence of time. Picture this. You're standing at the edge of existence itself. Scientists label it TO. Sounds harmless, right? Wrong. This single point marks the most explosive transformation reality has ever witnessed. But here's what's going to mess with your head. The word before completely loses meaning at this boundary. Not because we don't know what happened, but because time itself hadn't been invented yet. Think about your morning routine. You wake up, time passes, you grab coffee, more time flows by. Everything you experience happens in sequence. One thing after another. That's time, right? Now imagine all of that gone. Not frozen, not paused, just completely absent. No yesterday bleeding into today. No future waiting around the corner. No duration whatsoever. Your brain probably just glitched trying to process that. That's normal. Our minds evolved in a universe where cause comes before effect, where memories point backward and plans point forward. We're hardwired for time. But at TO, none of that existed. The cosmic stage hadn't been built yet. There was no when for anything to happen in. And here's where it gets wild. Einstein's equations, those mathematical masterpieces that describe how gravity bends space and how time stretches near massive objects. They work flawlessly everywhere in our universe. Anywhere you point a telescope, Einstein's math checks out with ridiculous precision. Except at TO. Right at that boundary, the equations crash harder than a computer trying to divide by zero. They spit out infinities, impossible answers, mathematical nonsense. It's like the universe installed a firewall written in the language of physics itself. A giant do not enter sign that even our best mathematical tools can't bypass. But why? What's the universe hiding behind that wall? Some physicists think TO isn't really a beginning at all. It's more like a transition point. Imagine a phase change, like ice melting into water. The ice doesn't really begin when it becomes liquid. It transforms. Maybe our universe underwent something similar. A transformation so radical that everything we call reality, space, time, matter, energy, emerged from something that existed in a completely different way. But if that's true, what was doing the transforming? What was there to transition from? This is where your intuition starts screaming for answers that might not exist. At least, not in any form we'd recognize. Let's try a thought experiment. Imagine you're describing the color red to someone who's never seen color. Not blind, they've just never experienced wavelengths of light reflecting off surfaces. You'd struggle, right? You might say it's like warmth, or passion, or danger. But none of those descriptions actually capture what red is. You're using concepts from their world to describe something outside it. That's exactly what we're doing when we ask about TO. We're using concepts like happened and existed and before that only makes sense. AFTER, time begins. We're trying to describe temporal color to beings who only learned to see after the first tick of the cosmic clock. Quantum fluctuations and the impossibility of true nothing. Now, let's talk about nothing. And I mean really talk about it. Because it turns out, nothing isn't what you think it is. In fact, nothing might be impossible. Empty your coffee cup. Pour it out completely. What's left inside? Nothing. Right. Wrong. Dead wrong. Physics reveals something that sounds like magic, but it's stone-cold experimental fact. What we call empty space is actually buzzing with invisible activity that never, ever stops. Head out to the deepest void between galaxies. We're talking about regions so empty you might find one single atom per cubic meter. That's emptier than any vacuum chamber we can build on Earth. And yet, even there, space itself refuses to stay quiet. It seethes, it bubbles, it crackles with energy at scales too small and too fast for us to see directly. Scientists discovered this when they tried to cool things down to absolute zero. That's negative 460 degrees Fahrenheit, the coldest possible temperature. The point where, theoretically, all motion should stop. All energy should drain away. Everything should become perfectly, absolutely still, except it doesn't. The energy never quite reaches zero. Even at that extreme cold, quantum fields keep vibrating. It's like trying to calm a pot of water on the stove. You turn off the heat, the big bubbles stop, the violent boiling settles down. But if you look close enough, you'll see tiny bubbles still forming at the bottom. Little pockets of vapor appearing and popping constantly. The quantum vacuum works the same way. Beneath the calm surface of empty space, constant creation and destruction churns away at scales smaller than atoms. These aren't just theoretical predictions. We can measure this stuff. There's an experiment called the Casimir effect that proves empty space exerts real, measurable force. Take two metal plates, bring them incredibly close together in a vacuum. I'm talking distances smaller than a red blood cell. The quantum fields between those plates have less room to fluctuate than the fields outside. This creates an actual pressure difference. The plates get pushed together by nothing, by literal empty space. Think about that for a second. Emptiness has weight. Vacuum has pressure. Nothing pushes on things. But here's where it connects to our cosmic origin story. These quantum fields filling every cubic inch of space. They can borrow energy from the future to create pairs of particles that pop into existence, dance briefly together, then annihilate and vanish. This happens trillions upon trillions of times every second in the space around you right now, in your body, in your brain, everywhere. The borrowed energy gets paid back so fast, the universe's bookkeeping system never catches the debt. It's like taking out a loan for 1/10000000th of a second. The bank doesn't even notice. Now scale that up, way up. What if our entire observable universe is one of these quantum fluctuations? A cosmic energy loan that got so big, so fast, it escaped the repayment deadline. The debt became real, permanent. And so did we. Some physicists seriously propose this. That our universe, with its trillion galaxies and its 100 billion trillion stars, started as a quantum hiccup in a vacuum that might have been all that existed. Or maybe it wasn't even a vacuum as we understand it. Maybe it was something deeper, something more fundamental that we don't have words for yet. But if a vacuum can fluctuate and create a universe, what's the vacuum sitting in? What provides the quantum fields that do the fluctuating? It's turtles all the way down, except the turtles are made of math and probability and they might go on forever. This forces us to consider whether different layers of nothingness exist. Maybe there's shallow nothing, the quantum vacuum with its zero-point energy and virtual particles, then deeper nothing beneath that, and even deeper nothing below that level. Each layer somehow more nothing than the one above, until we hit something so fundamentally empty that even quantum mechanics doesn't apply anymore. Or maybe we never hit bottom. Maybe nothingness has infinite depth, with our universe floating somewhere in the middle layers, like a fish that doesn't know it's in water. Some radical thinkers suggest mathematics itself might be the foundation beneath everything, not numbers scribbled on paper, not equations taught in classrooms, but pure mathematical relationships that exist independently of physical reality. Relationships that just are, whether anyone's around to think about them or not. In this view, our universe isn't made of matter and energy doing a complicated dance. It's made of mathematical patterns that achieved enough complexity to experience themselves. You're not biology plus chemistry plus physics. You're an equation that became self-aware. A mathematical structure so intricate it learned to feel and think and wonder about its own origins. Does that idea make you uncomfortable? It should. It suggests that everything solid, everything real, everything you can touch and taste and see is ultimately abstract. Pure information given form. The universe is less like a machine and more like a theorem proving itself into existence. But other scientists point in a completely different direction. They suggest consciousness plays the fundamental role. That observation by aware beings doesn't just reveal reality, it creates reality. In quantum mechanics, particles exist in multiple states simultaneously until something measures them. The act of measurement forces the universe to choose to collapse infinite possibilities into one concrete outcome. Could conscious observation be the mechanism that creates existence itself? If so, then before any observers emerged, the universe would have existed in a fuzzy cloud of maybe this, maybe that, pure potential without actuality. The first spark of awareness anywhere in the cosmos would have been the true moment of creation. The instant when some of those maybes collapsed into definite is. This leads to a brain-twisting question. If consciousness creates reality by observing it, and if it took billions of years for conscious observers to evolve, what was the universe doing all that time? Was it waiting in quantum limbo for someone to notice it? Or does observation somehow reach backward through time, retroactively solidifying a past that was uncertain until someone existed to remember it? Cosmic inflation and the birth of everything. Let's zoom in on that first fraction of a second after TO. That's when something truly bizarre happened. Something that explains why the universe looks the way it does today, but raises even deeper questions about what triggered it all in less than 1/trillionth of a trillionth of a trillionth of a second. A microscopic bubble of space expanded faster than light itself, not faster than things moving through space. That's still impossible. But space itself inflated so rapidly that distant points separated faster than light could travel between them. This process, called cosmic inflation, turned a region smaller than a proton into something the size of a grapefruit, then kept going. Imagine a soap bubble forming on the surface of still water, except the water doesn't exist yet. The surface doesn't exist yet. And somehow the bubble creates both water and surface as it grows. The bubble doesn't form in space. The bubble creates space by expanding. It generates distance, volume, and dimension from nothing as it inflates. This sounds like science fiction, but cosmic inflation elegantly solves real problems that plagued earlier models of the Big Bang. For one thing, it explains why the universe looks so uniform in every direction. Temperature measurements show that distant regions of space, regions so far apart they've never been in contact with each other, have almost identical properties. How did they coordinate? How did they end up matching so perfectly? Inflation provides the answer. Before the rapid expansion, All those now distant regions were once close together, close enough to reach thermal equilibrium, to smooth out their differences. Then inflation grabbed that tiny, uniform patch and stretched it to cosmic scales. The uniformity we see today is fossil evidence of intimate contact in the universe's first moments. Inflation also explains why space appears flat instead of curved. General relativity tells us that matter and energy curve space-time. Enough curvature and the universe would wrap back on itself like the surface of a sphere. But observations show our universe is remarkably flat, like an infinite sheet of paper rather than a ball. Why? Because inflation stretched it flat. Any curvature that existed before inflation got pulled so tight during that explosive expansion that from our perspective, space looks completely flat. It's like drawing a tiny circle on a balloon, then inflating the balloon to the size of Earth. From an ant's perspective standing on that circle, the surface would look perfectly flat, even though the overall structure is curved. But here's the part that should blow your mind wide open. If quantum fluctuations can trigger inflation once, creating our universe, what stops them from doing it again, and again, and again? The mathematics of inflation don't just allow for one universe. They practically demand infinite universes, because once inflation starts somewhere, it creates more space. And in that new space, quantum fluctuations keep happening. Some of those fluctuations trigger new inflation in localized regions. Those regions expand, creating more space, producing more quantum fluctuations, spawning more inflation bubbles. It becomes a runaway process. A cosmic chain reaction that never ends. Eternal inflation, physicists call it. And it suggests something profound and disturbing about our place in existence. We're not the universe. We're a universe. One bubble in an infinite foam of realities. Somewhere out there, right now, other big bangs are happening. Other cosmic inflations are launching. Other bubbles of space-time are erupting into existence with their own laws of physics, their own fundamental constants, their own possibilities for complexity and life. Most of those bubble universes would be stillborn. Their physical constants would make stars impossible, or atoms unstable, or expansion so rapid that structure never forms. They'd flash into existence and remain forever empty. Dead cosmoses with no one around to notice they exist. But occasionally, by pure chance, a bubble would have the right properties. Gravity strong enough to form galaxies, but weak enough to allow stars to burn slowly. Electromagnetism balanced precisely to permit complex chemistry. Nuclear forces tuned just right to produce the elements needed for life. We live in one of those rare bubbles. Not because we're special or chosen, but because we couldn't live anywhere else. The anthropic principle in action. We observe a life-friendly universe because only life-friendly universes produce observers. This raises uncomfortable questions about meaning and purpose. If infinite universes exist, each with random properties, then our universe's apparent fine-tuning isn't mysterious anymore. It's just selection bias. We're like lottery winners amazed at our luck, forgetting that someone had to win eventually. But eternal inflation suggests something even stranger. If new universes keep forming forever, then the process has no beginning and no end. Our Big Bang wasn't the start of everything. It was just one more burst in an eternal sequence of cosmic fireworks that has always been exploding and always will be. This means the question, what came before the Big Bang, has a simple answer in eternal inflation models. More inflation came before. Other universes being born, expanding, potentially dying. Our cosmic neighborhood might be ancient beyond imagination. with our particular bubble being a relatively recent addition to an infinite family of realities. Some versions of eternal inflation even suggest that information might leak between bubble universes under certain conditions. Quantum tunneling events could allow particles or fields to hop from one bubble to another, carrying traces of alien physics into our realm. We might never notice these intrusions because they'd be so rare and subtle, but they'd be there, hidden in the statistical noise of quantum measurements. Advanced civilizations in other bubble universes might have figured out how to send signals across the bubble boundaries. They might be broadcasting messages into the inflating space between bubbles, hoping someone in a neighboring reality picks up the transmission. These messages could take forms we'd never recognize as communication, because they'd be encoded in physics that doesn't quite match our own. Or maybe the boundaries between bubbles aren't as solid as we think. Maybe under extreme conditions, near black holes or during the final moments of a universe's life cycle, those boundaries become permeable. Conscious beings might be able to migrate from dying universes into fresh ones, carrying their knowledge and culture across cosmic generations. If consciousness can survive the transition between bubble universes, then perhaps advanced civilizations have been doing this for timeframes that dwarf our universe's age. There might be ancient minds out there, refugees from bubble universes that formed and died countless cosmic generations ago. They might have witnessed the birth and death of thousands of realities, accumulating wisdom beyond our ability to comprehend. These elder consciousnesses could be embedded in our universe right now, hiding in plain sight or operating at scales we can't perceive. They might have technologies that manipulate the quantum vacuum itself, triggering new inflation events deliberately rather than waiting for random fluctuations. In that case, our Big Bang might not have been natural at all. It might have been engineered by beings from a previous cycle of existence. This idea connects to ancient questions about cosmic purpose and design. Not religious creation in the traditional sense, but something equally profound. The possibility that intelligence and consciousness aren't accidental byproducts of random cosmic evolution, but instead represent a fundamental creative force that has been shaping reality for eternity. If true, then we're not alone in any meaningful sense. We're part of an infinite community of conscious beings spread across bubble universes, each exploring different regions of possibility space, each learning different lessons about existence, each contributing to a grand project of universal self-understanding that transcends individual realities. The multiverse stops being a cold, impersonal concept and becomes a living ecosystem of minds and possibilities. Your thoughts, right now, might be contributing to patterns of consciousness that ripple across bubble boundaries through mechanisms we don't yet understand. Every choice you make could influence the probability distributions that govern quantum fluctuations in neighboring realities. In this view, consciousness isn't an observer of cosmic history, it's a participant in cosmic creation. And the question of what came before our Big Bang dissolves into a deeper question. What role does awareness play in generating the infinite cascade of universes from the quantum substrate of possibility itself? That question points us toward the next layer of mystery, where we'll discover that the empty space around us isn't empty at all, that virtual particles pop in and out of existence constantly, and that the boundary between real and unreal might be far thinner than anyone suspected. But we're getting ahead of ourselves. Right now, sitting wherever you are, you're surrounded by the aftermath of that cosmic inflation event. Every atom in your body, every photon hitting your eyes, every thought firing through your neurons, traces its lineage back to that first trillionth of a second. You're not separate from the Big Bang. You're the Big Bang still happening, still unfolding, still creating new complexity 14 billion years later. And if eternal inflation is right, somewhere in the infinite foam of realities, another version of you is reading a slightly different version of these words in a universe where physics works just a little bit differently. Maybe their gravity's a touch stronger, making stars burn faster. Maybe consciousness emerged earlier in cosmic history. Maybe the beings reading these words aren't even human, but they're asking the same questions we are. Where did we come from? What existed before? Why is there something rather than nothing? These questions seem to be written into the fabric of consciousness itself. Regardless of which bubble universe you happen to be in, the search for answers drives us to probe deeper into the quantum nature of reality itself, to understand not just what happened at TO, but what TO really means, whether time had a beginning or whether it's an illusion that emerges from something timeless and eternal, whether our universe is a singular miracle or one note in an infinite cosmic symphony that's been playing forever and will never stop. As we stand at this boundary between the knowable and the impossible, between science and philosophy, between answers and deeper questions, one thing becomes clear. The universe is stranger than we imagined, stranger than we can imagine with our current concepts and categories. And that strangeness isn't a bug in our understanding. It's a feature of reality itself. The cosmos doesn't owe us comprehensible answers. It doesn't have to make sense to creatures who evolved on one small planet to survive and reproduce. The fact that we can ask these questions at all, that we can peer back to the edge of time and glimpse what might lie beyond, is itself miraculous. We're the universe's way of knowing itself. And maybe that's the closest we'll ever get to understanding what came before everything began. Part 2. The hidden world within the quantum vacuum. Remember how we talked about nothing being impossible? Well, buckle up, because what we're about to explore makes that idea look tame. Right now, as you're reading this, invisible particles are blinking in and out of existence inside your body. Not metaphorically, actually happening. These ghostly entities appear, exist for impossibly brief moments, then vanish without leaving a trace. And without them, you wouldn't exist. Stars wouldn't shine, atoms couldn't hold together. Reality as we know it would collapse. The quantum vacuum and zero-point energy. Let's start with something that sounds simple but gets weird fast. Energy. You probably think of energy as something you can use up. Burn gasoline, release energy. Eat food, get energy. Run out of fuel, run out of energy. Simple, right? Wrong. There's a type of energy that can never run out. Energy that exists even when you've removed everything else. Scientists call it zero-point energy, and it's one of the strangest discoveries in physics. Here's how they found it. Imagine you've got a container. You pump out all the air molecules, every last one. You cool it down to absolute zero. That's negative 460 degrees Fahrenheit. At this temperature, according to classical physics, everything should stop moving. All thermal motion should cease. The energy inside should hit exactly zero. But when physicists actually measured these ultra-cold, ultra-empty containers, they found something shocking. The energy never reaches zero. It gets close, really close, but always stays above zero. There's this baseline energy that refuses to disappear no matter what you do. Think of it like trying to delete all the files on a computer. You can delete your documents, your photos, your programs, but there's always operating system code running in the background that you can't remove. The quantum vacuum works the same way. It has background energy that's built into the fabric of space itself. This zero-point energy isn't just sitting there doing nothing, it's constantly creating and destroying virtual particles. These aren't science fiction inventions, they're real quantum entities that pop into existence in particle and antiparticle pairs, exist for incredibly brief moments, then collide and annihilate each other. The lifetime of these virtual particles depends on how much energy they borrow. The more energy they grab from the quantum vacuum, the shorter they can exist before they have to pay it back. Some virtual particles live for only 0.000000000000000000000000000000000001 seconds. That's a decimal point, followed by 23 zeros, and then a 1. Your brain can't really process timescales that short. Nothing in your daily experience comes close. Light, the fastest thing in the universe, travels about 1 foot in a billionth of a second. In the lifetime of the shortest-lived virtual particles, light doesn't even make it across a single atom. But here's what makes this really mind-bending. These virtual particles aren't just theoretical predictions. They produce measurable effects in the real world. There's an experiment that proves this beyond any doubt. Take 2 metal plates, make them incredibly smooth and flat, place them in a vacuum chamber and pump out all the air. Now bring them close together. Really close. We're talking distances of less than 1/1000th of a millimeter. That's about 100 times thinner than a human hair. What happens? The plates get pushed together by an invisible force. This is the Casimir effect, named after Dutch physicist Hendrik Casimir, who predicted it in 1948. The force is tiny, about the weight of a single drop of water spread across an area the size of your hand. But it's measurable, repeatable, and undeniably real. Here's why it happens. Between the plates, only virtual particles with wavelengths smaller than the gap can exist. But outside the plates, virtual particles of all wavelengths can form. This creates a pressure difference. More quantum activity outside means more pressure pushing inward. Empty space literally squeezes the plates together. This proves something profound. The quantum vacuum isn't empty in any meaningful sense. It's a seething ocean of energy and activity, constantly churning at scales too small for us to see directly. We're not surrounded by nothingness. We're immersed in a quantum soup that never stops bubbling. Now scale this up, way up. If virtual particles can pop into existence in the quantum vacuum around us, what about in the vacuum that existed before our universe? Or instead of before, since time didn't exist yet? Let's say in the deeper layer of reality from which our universe emerged. Could our entire cosmos be a quantum fluctuation that got lucky? A virtual universe that borrowed enough energy to inflate beyond the point where it had to pay the debt back. The math actually supports this idea. In quantum mechanics, the uncertainty principle allows for enormous energy fluctuations as long as they're brief enough. A fluctuation big enough to create a universe is technically allowed. It just has to happen fast. But if inflation kicks in quickly enough, the fluctuation grows faster than the payback deadline. It becomes permanent, real, actual, instead of virtual. Our universe might be the quantum equivalent of a loan that grew too big to collect on. This raises a disturbing question. If one universe can fluctuate into existence from the quantum vacuum, what's stopping others from doing the same thing constantly? The answer might be nothing. New universes could be popping into existence all the time, each one starting with its own Big Bang, each one inflating into its own separate reality. We'd never know they were there because they'd be causally disconnected from us. No signal from those other universes could ever reach us. They exist in their own bubbles of space-time, separated from our bubble by regions of quantum vacuum that keep spawning more bubbles. It's an infinite fractal of existence, with universes within universes within universes, all the way down and all the way up, virtual particles and the nature of reality. Let's dig deeper into these virtual particles, because they're not just curiosities. They're fundamental to how reality works at its deepest level. Every force you experience, every interaction between particles, gets carried by virtual particles. When an electron repels another electron through electromagnetic force, virtual photons are doing the pushing. These aren't the photons you see with your eyes. They're quantum messengers that exist for too short a time to be observed directly. When quarks bind together to form protons and neutrons in atomic nuclei, virtual gluons carry the strong nuclear force between them. These virtual gluons pop in and out of existence billions of times per second, constantly reinforcing the bonds that hold matter together. Without virtual particles, atoms would fly apart. Chemistry would be impossible. Stars couldn't exist. Planets couldn't form. Life would never get started. Everything you see, touch, or interact with depends on this invisible quantum machinery operating beneath the surface of reality. But here's where it gets truly strange. Under certain conditions, virtual particles can become real. The boundary between virtual and actual isn't as solid as you might think. Near black holes, something remarkable happens. The intense gravitational field can separate virtual particle pairs before they annihilate each other. One particle falls into the black hole while its partner escapes into space. The escaping particle becomes real, carrying away energy from the black hole in the process. This is Hawking radiation, named after Stephen Hawking, who discovered it in 1974. It means black holes aren't completely black. They glow with quantum radiation produced by virtual particles being promoted to real particles at the event horizon. Over immense timescales, this process causes black holes to evaporate. They slowly lose mass through Hawking radiation until eventually they disappear completely in a final burst of energy. Even the most massive black holes, billions of times heavier than our sun, will eventually evaporate. It just takes an absurdly long time. We're talking 10 to the 100 years or more. That's a 1 followed by 100 zeros. For comparison, the current age of the universe is only about 14 billion years. That's 14 followed by 9 zeros. Black hole evaporation operates on timescales that make the entire history of the universe so far look like a brief instant. But the key point is this: virtual particles can become real when given enough energy. And if our universe started as a quantum fluctuation, then everything we call real planets, stars, galaxies, people, might still be virtual in some deeper sense. We could be living in a cosmic quantum fluctuation that hasn't collapsed yet. Some physicists take this idea seriously. They propose that our universe is borrowing its energy from a deeper level of reality we haven't discovered. We exist on borrowed time, in borrowed space, with borrowed energy. The whole show could theoretically collapse back into the quantum vacuum if the cosmic bookkeeping ever catches up with us. Now, you might be wondering, if that's possible, why hasn't it happened already? We've been around for 14 billion years. Surely that's enough time for the universe to realize it's violating quantum mechanics and collapse back to nothing. The answer involves cosmic inflation again. When our universe inflated in that first fraction of a second, it created so much space, so much distance, so much volume that the total energy became genuinely positive instead of borrowed. Inflation didn't just make our universe bigger. It made it real in a way it wasn't before inflation kicked in. Think of it like this. You take out a small loan to start a business. Initially, you're in debt, but if the business grows fast enough and becomes profitable, you can pay back the loan and still have money left over. The initial borrowed capital becomes real wealth through growth. Cosmic inflation did something similar for our universe's energy, the multiverse theory and colliding universes. Now we're ready to tackle one of the biggest ideas in modern cosmology, the multiverse. Not just multiple universes existing separately, but a vast cosmic ecosystem where universes can interact, collide, and influence each other in ways we're only beginning to understand. If quantum fluctuations created our universe, and if those fluctuations are happening constantly in the quantum vacuum, then new universes must be forming all the time. Each one would start with its own Big Bang. Each one would undergo its own period of cosmic inflation. Each one would develop its own unique properties. Picture an ocean where bubbles constantly form on the surface. Each bubble represents a universe. Most bubbles pop quickly, universes with physics that doesn't allow stable matter. But some bubbles persist and grow. Universes where the fundamental constants happen to fall within ranges that permit complexity. Our universe is one bubble in this cosmic ocean. We can't see other bubbles directly because they're expanding away from us faster than light can travel. Cosmic expansion creates an information barrier that prevents us from detecting neighboring universes under normal circumstances. But what if bubbles form close enough together that they touch before expansion separates them? What if two universes collide? This isn't science fiction speculation. It's a testable prediction of eternal inflation theory. If bubble universes keep forming in the inflating space around us, eventually some of them should bump into our bubble, and when they do, they'd leave detectable traces. The collision would create a circular pattern in the cosmic microwave background radiation. That's the ancient light from our universe's early moments that still fills the sky in every direction. A universe collision would appear as a subtle, warm or cool spot in this radiation, like a bruise marking where another reality touched ours. Several research teams have claimed to find such patterns in cosmic microwave background data. The evidence isn't conclusive yet. The signals are so faint and subtle that it's hard to distinguish them from random fluctuations or instrumental noise. But the search continues, and telescope technology keeps improving. If we do confirm evidence of universe collisions, it would revolutionize our understanding of cosmic origins. It would prove that our universe isn't alone, that other realities exist beyond the edge of what we can observe, that the multiverse isn't just a theoretical possibility, but an established fact. But universe collisions might do more than leave visible traces. They might allow information transfer between realities. Quantum fields could carry data across the collision boundary, creating a form of interdimensional communication that we've never imagined. Advanced civilizations in neighboring universes might be trying to send messages through these collision zones. They could encode information in the quantum structure of fields that leak from their universe into ours during brief moments of contact. We might be receiving alien transmissions right now without realizing it, buried in data we interpret as background noise. Or consider this possibility. If consciousness is a quantum phenomenon, as some theories suggest, then maybe awareness itself can tunnel between colliding universes. Your consciousness might occasionally pick up echoes from parallel versions of yourself living in nearby bubble universes that briefly touched our reality. Ever experienced déjà vu? That eerie feeling that you've lived through a moment before, even though you know you haven't. Maybe that's not a glitch in your brain's memory system. Maybe it's your consciousness briefly resonating with a parallel version of yourself in a universe that collided with ours at some point in the past. This is pure speculation, of course, but it's grounded in legitimate physics. If eternal inflation is real, and if universes can collide, and if quantum information can transfer across boundaries, then these possibilities become at least theoretically plausible. The cyclic universe, model, and cosmic rebounds. Now let's explore a completely different answer to what came before the Big Bang. What if our universe didn't begin at all? What if it's been here forever, cycling through endless rounds of expansion, collapse, and rebirth? The cyclic universe model proposes that our cosmos undergoes a repeating pattern. Right now, we're in an expansion phase. Galaxies are moving apart, space is growing, the universe is getting bigger and cooler. But according to cyclic models, this expansion won't continue forever. Eventually, the expansion will slow down and stop. Then gravity takes over and pulls everything back together. Galaxies collide and merge. Stars get stripped from their orbits. Matter compresses as the universe shrinks. Temperature rises as compression heats everything up. The cosmos collapses toward what seems like total destruction. But here's the twist. Instead of ending in annihilation, the collapse triggers a rebound. The universe bounces back, like a ball hitting the ground and springing upward again. The compression reaches a maximum density, then expansion begins anew. What looks like a big bang from inside the universe is really just the bounce point between collapse and expansion. This model has several advantages. It eliminates the uncomfortable question of what caused the Big Bang, because there was no ultimate beginning. The universe has always existed, cycling through phases that we mistake for beginnings and endings. It also explains why our universe appears so uniform in temperature and density without requiring incredibly rapid inflation. If our current expansion phase emerged from a previous contraction phase, the uniformity is explained by mixing that occurred during the collapse. Think of it like a cosmic trampoline. The universe falls toward the trampoline surface, accelerating as it approaches maximum density. Then the trampoline's elasticity kicks in, launching the universe back up into a new expansion cycle. From our perspective inside the universe, each bounce looks like a big bang, even though it's really just another oscillation in an eternal rhythm. Recent observations complicate this picture, though. We've discovered that cosmic expansion is accelerating, driven by mysterious dark energy that pushes space apart. This acceleration seems to rule out a future collapse. If expansion keeps speeding up, gravity will never win the tug-of-war needed to trigger a big crunch. But cyclic theorists have adapted their models. They propose that dark energy strength changes over cosmic timescale. Maybe it's strong now, driving acceleration. But billions or trillions of years in the future, it might weaken or even reverse, eventually allowing gravity to halt expansion and begin contraction. In some versions of cyclic cosmology, each cycle lasts about 1 trillion years. Our current cycle began 14 billion years ago, making us relatively young in cosmic terms. We have hundreds of billions of years left before expansion stops and collapse begins. Plenty of time for civilizations to rise, flourish, and prepare for what comes next. But here's a fascinating question. Does each cycle produce an identical universe, or do small changes accumulate over cosmic generations? Maybe the fundamental constants shift slightly from one cycle to the next. Maybe the laws of physics evolve. Maybe information somehow carries over from one cosmic generation to the next, allowing the universe to learn and develop over countless cycles. If information persists through the bounce, then advanced civilizations might find ways to send messages to their successors in the next cycle. They could encode knowledge in the quantum structure of space itself, creating cosmic time capsules that survive the collapse and rebound. Future civilizations in the next cycle would discover these messages and learn that they're not the first intelligent beings to inhabit their universe. This raises profound questions about the arrow of time. If the universe cycles eternally, with no beginning and no end, then past and future lose some of their meaning. The universe is less like a story with a beginning, middle, and end, and more like a circle that keeps rotating forever. Some cyclic models go even further. They propose that multiple universes take turns expanding and contracting, like cosmic pistons in an infinite engine. While our universe expands, others contract. While others bounce and begin new expansion phases, we coast through our current growth period. The multiverse becomes a vast machine with countless parts moving in coordinated rhythms. In this view, what came before our Big Bang has a straightforward answer: the previous cycle. But this just pushes the mystery deeper. What started the eternal cycling in the first place? Is there a meta-cycle that governs when cycling begins and ends? Or does the cycling go back infinitely with no first cause, no ultimate origin, no starting point? These questions bring us face to face with infinity, a concept that breaks our intuitions in fascinating ways. Can the past be infinite? Can there be an infinite sequence of causes stretching backward forever? Or must there be a first cause, a beginning that itself had no cause? Philosophy and physics collide at this boundary, and the answers might reveal something profound about the relationship between time, causation, and existence itself. Something we'll explore deeper as we continue this journey into the heart of cosmic origins. But first, we need to talk about dimensions you can't see, strings too small to measure, and membranes floating in higher dimensional space. Because according to string theory, our universe might be even stranger than we've imagined so far. Part 3: Hidden Dimensions and String Theory. The invisible architecture of reality. Right this second, you're surrounded by dimensions you cannot see, touch, or even imagine. They're not somewhere else in the distant cosmos. They're here, wrapped around every atom in your body, coiled so tightly that the most powerful microscopes ever built couldn't detect them. According to string theory, our familiar 3 dimensions of space are just the visible surface of a reality that contains 10 or 11 total dimensions. Think about that for a moment. We spend our entire lives moving through a universe that's far larger and stranger than anything our senses can perceive. Picture a tightrope stretched between 2 buildings. From a distance, it looks one-dimensional, just a thin line cutting through space. But zoom in close enough, and you discover that rope has hidden dimensions, circular paths wrapped around its length that an ant could walk along. String theory suggests the fabric of our universe works exactly the same way. What appears to be empty space actually contains 6 or 7 extra dimensions, curled up so small that they exist at every point around us but remain completely invisible. These aren't abstract mathematical constructs. These hidden dimensions are dynamic, shape-shifting arenas where the fundamental forces of nature play out their cosmic drama. The strength of gravity pulling you toward Earth right now depends on how these invisible dimensions are curved and twisted. The electromagnetic force binding the atoms in your body together reflects the geometry of spaces you'll never see. Even the nuclear forces holding atomic nuclei together derive their properties from these hidden realms. Now here's where it gets truly wild. In string theory, the smallest building blocks of reality aren't particles at all. They're tiny vibrating loops of pure energy called strings. These strings are unimaginably small, about 100 billion times smaller than a proton. That's so incredibly tiny that if you scaled an atom up to the size of our solar system, a single string would still be smaller than a tree on Earth. Yet everything in the universe, from the chair you're sitting on to the distant galaxies billions of light years away, is made of these infinitesimal vibrating loops. Each different vibration pattern creates what we perceive as a different particle. An electron is a string vibrating one particular way. A photon is the same type of string, just vibrating at a different frequency. Quarks, neutrinos, every fundamental particle in the standard model of physics emerges from different vibrational modes of these cosmic strings. It's like a symphony where every note represents a different building block of matter. And the entire universe is the music these strings compose as they vibrate through hidden dimensions. But string theory does more than just describe particles. It completely transforms how we think about the Big Bang itself. Remember how we said traditional physics breaks down at the moment of creation, producing infinities and impossible answers? String theory might solve that problem by revealing what triggered the Big Bang in the first place, colliding universes and the birth of reality. Our entire universe could be a three-dimensional membrane floating in a higher dimensional space. Scientists call these membranes brains, and they exist in dimensions beyond our ability to perceive. Imagine our universe as a vast soap film stretched across the surface of a multi-dimensional bubble. Every galaxy, every star, every atom exists on this three-dimensional surface, unable to move into the higher dimensions that surround it. Now imagine another brain, another complete universe with its own space and physical laws, floating nearby in this higher dimensional realm. These two cosmic membranes drift through dimensions we cannot see, and occasionally they collide. When two brains crash together, the impact releases enormous amounts of energy into each membrane. From our perspective, trapped inside one of these brains, this energy release looks exactly like a Big Bang. Space and time, as we experience them, begin at the moment of collision. The cosmic inflation that stretched our universe in a fraction of a second could be energy from a brain collision, rippling through our dimensional membrane. Think about what this means. What we call the Big Bang wasn't creation from absolute nothingness. It was a transition triggered by contact with a parallel universe we can never directly observe. The brains themselves existed before the collision. Time within our brain began at impact, but the higher dimensional reality had no such beginning. This brain collision model explains several cosmic mysteries. It accounts for why the cosmic microwave background radiation appears so uniform in every direction we look. If our Big Bang was an energy release from a brain collision, the uniformity comes naturally from how the impact energy spread across our membrane. The model also suggests something even more mind-bending. Those hidden dimensions might contain multiple parallel brains, each hosting its own universe. These parallel realities could be as close as a millimeter away from us in higher dimensional space, yet completely unreachable because we're trapped on our three-dimensional brain. What if you could perceive these higher dimensions? You'd see parallel universes stacked around ours like pages in an infinite book, each one a complete cosmos with its own galaxies and physical laws. Some might have stronger gravity, making stars burn faster. Others might have weaker electromagnetic forces, preventing complex chemistry from developing. A few might be eerily similar to ours, with Earth-like planets and possibly even alternate versions of human civilization. If brain collisions can create Big Bangs, they might still be happening somewhere in the higher dimensional space that contains our brain. New collisions could be triggering new universes right now. Scientists are searching for evidence of these brain interactions in the cosmic microwave background radiation. Finding such patterns would be direct evidence that parallel universes exist and that our reality extends far beyond the 3 dimensions we can perceive. The eternal cosmic engine. While string theory and brain collisions offer one explanation for cosmic origins, another theory suggests something even more extraordinary. What if Big Bangs aren't rare events but constant occurrences happening everywhere, all the time? Traditional inflation theory explains how our universe grew from subatomic to cosmic size in its first fraction of a second, but eternal inflation suggests this process never stops. Picture a pot of boiling water where bubbles constantly form and break free. Each bubble represents a complete universe, like ours. The boiling water represents the inflating field that fills the multiverse, forever creating new bubbles of reality. Our observable universe is just the inside of one such bubble. What we call the Big Bang was the moment when our local region stopped inflating and began the slower expansion we observe today. But outside our bubble, beyond the cosmic horizon we can never reach, the inflation field continues its exponential growth. Occasionally, it spawns new pocket universes, each experiencing its own Big Bang. This process has no beginning and no end. Once inflation begins, the mathematics show it produces infinite future time and infinite space. Each pocket universe could have different physical constants. In some, gravity might be 10 times stronger, causing stars to burn through their fuel in millions of years instead of billions. In others, the electromagnetic force might be weaker, preventing atoms from bonding into molecules. The vast majority of these pocket universes would be sterile, lifeless expanses where nothing interesting ever happens. But occasionally, by pure chance, a pocket universe would emerge with physical constants falling within the narrow ranges that allow for complexity and potentially conscious life. We live in one of these rare universes, not because of design or cosmic purpose, but simply because we couldn't exist in any other type. The distances between pocket universes are staggering beyond comprehension. They're separated by regions of still inflating space that grow faster than light can cross them. Even if you could travel at light speed for trillions of years, you would never reach another pocket universe. The space between you and it would expand faster than you could traverse it. Yet, in an eternally inflating multiverse, every possible combination of physical constants must exist somewhere. There's a pocket universe where the speed of light is different. There's another where quantum mechanics works slightly differently. Everything that can happen does happen in some pocket universe. Some physicists worry that eternal inflation makes science impossible by predicting that literally anything can happen somewhere. Others embrace it as the most elegant explanation for why our universe seems so perfectly tuned for complexity. We don't need to invoke design or purpose. We just need to recognize that in an infinite multiverse containing all possibilities, observers will always find themselves in universes capable of producing observers. The mathematics of everything. But even eternal inflation leaves deeper questions unanswered. At the edge of the Big Bang, at the very boundary where space and time themselves began, all our equations break down completely. Physicists have traced our universe's history back to within a tiny fraction of a second after the beginning. But there's one boundary they absolutely cannot cross. Scientists call this the Planck epoch, lasting from time zero to an incomprehensibly brief moment after the Big Bang began. During this interval, the universe was so hot and dense that quantum effects dominated even gravity itself. At the Planck scale, the smooth fabric of space-time that Einstein described gets shredded into what physicists call quantum foam. Space and time become grainy and uncertain, like a photograph enlarged until you can see the individual pixels. Think of trying to use a ruler made of atoms to measure something smaller than an atom. The ruler itself becomes the limiting factor. At the Planck scale, we face the same problem but far more fundamentally. We're trying to use concepts of space and time to understand the origin of space and time themselves. This creates what physicists call the boundary problem. Every equation in physics assumes that space and time exists as a background framework where events can unfold. But at the moment of the Big Bang, there was no framework. Einstein's general relativity predicts that all matter was compressed into a mathematical point of infinite density called a singularity. But infinities in physics usually mean a theory has reached its limits. String theory offers a potential solution. It suggests that what we call the Big Bang singularity should be replaced by something else. Perhaps a region of maximum possible density where space and time become quantized, broken into discrete units. In this view, there would be no infinitely small point, no moment of true nothingness. Instead, space-time would have a minimum size determined by string theory's fundamental length scale. The hidden dimensions that string theory predicts might have played a crucial role in this process. During the Planck epoch, all dimensions might have been wrapped up together at the smallest possible scale. As the universe expanded and cooled, 3 dimensions unwrapped and grew large, while the others remained tightly curled. Why only 3 dimensions expanded while others stayed small remains one of string theory's deepest mysteries. Some versions of string theory suggest that the Big Bang might represent a dimensional transition, a moment when the geometry of space itself underwent a fundamental transformation. This dimensional transition could have released the enormous energy that drove cosmic inflation and created all the matter and energy in our observable universe. As we push deeper into these questions, we're forced to confront the relationship between mathematics and physical reality itself. Are the equations we write down merely descriptions of a physical universe that exists independently, or is the universe itself fundamentally mathematical in nature? Could reality be made not of matter and energy, but of pure mathematical relationships? The hidden dimensions that string theory reveals aren't just mathematical curiosities. They're fundamental aspects of reality that shape everything we experience. From the forces binding atoms together to the cosmic evolution that allowed life to emerge, understanding these dimensions might be the key to finally answering the ultimate question. Why is there something rather than nothing? Think about where we've traveled so far. We started by questioning what existed before time itself began. We discovered that empty space seethes with quantum activity. We explored how parallel universes might be crashing into ours. And now we've seen how hidden dimensions beyond our perception might hold the key to cosmic creation. But the deepest mysteries still lie ahead, where the boundary between observer and observed, between mind and matter, becomes impossible to distinguish. Part 4: Consciousness, Observation, and the Structure of Reality. The Observer, Effect, and Quantum Reality. Right now, as you focus on these words, you might be doing something far more profound than simply reading. You might be actively creating the reality you're observing. This isn't mysticism, it's quantum mechanics, revealing something shocking about the relationship between consciousness and the physical universe. In the quantum world, particles don't behave like solid objects. Before anyone observes them, they exist in multiple states simultaneously. An electron can spin in multiple directions at once. A photon can travel through multiple paths at the same time. These are fundamental features of reality itself. Think about the famous double-slit experiment. When scientists fire electrons through two narrow slits, something impossible happens. Each electron goes through both slits simultaneously, interfering with itself and creating a distinctive pattern. But here's where it gets strange. The moment you observe which slit the electron goes through, everything changes. The interference pattern disappears. The electron behaves like it went through only one slit. This isn't about disturbing the electron with equipment. Even when experiments don't physically interfere with the particle, observation still collapses quantum possibilities into a single reality. Something about consciousness, looking at the quantum world, forces it to choose one definite state. Now think about cosmic origins. If observation creates reality at the quantum level, what happened before conscious observers evolved? For billions of years after the Big Bang, no minds existed to collapse quantum possibilities. Did the universe exist in superposition until the first conscious beings appeared? Some physicists propose exactly that. The early universe remained suspended in quantum uncertainty until consciousness emerged. In this view, the fact that we exist now, looking back at cosmic history, might be what selected which version of the Big Bang occurred. Our observations today could reach backward in time, determining which quantum possibilities became real billions of years ago. This creates a cosmic loop where the end determines the beginning. Conscious observers in the present collapse the quantum possibilities of the past. But those past possibilities had to be tuned to allow conscious observers to emerge. The universe might be a self-consistent loop where consciousness and cosmos create each other. But if consciousness plays this fundamental role, we need to ask where it comes from and how it connects to the deeper fabric of reality, the holographic universe and information reality. Everything you think is solid might be an illusion. According to the holographic principle, you might be observing a projection from information stored on a distant two-dimensional surface, billions of light years away. This idea emerged from studying black holes. When matter falls into a black hole, quantum mechanics says information can never be destroyed. The solution was startling. Information doesn't disappear inside. It gets encoded on the black hole's two-dimensional surface. Physicists realized this principle might apply to the entire universe. All information in any three-dimensional region could be encoded on the two-dimensional boundary of that region. Our universe might work like a hologram, with everything we experience as three-dimensional depth actually being a projection from a cosmic boundary. From this perspective, distance corresponds to quantum entanglement between boundary regions. Space emerges from patterns of entanglement in the underlying two-dimensional reality. We're not moving through space. We're experiencing different configurations of quantum information. This transforms how we think about the Big Bang. If our universe is a projection, the Big Bang represents when information processing began on the cosmic boundary. Before this, the boundary existed in a dormant state, containing potential but not yet projecting it. The boundary itself might be eternal. What we call cosmic history would be information states playing out on this timeless surface. But here's the most profound implication. If reality is holographic, then separation between different conscious beings might be illusion. All observers might be aspects of a single information processing system experiencing itself from multiple perspectives. The boundary between self and universe dissolves in ways we're only beginning to understand. Time as illusion and emergent experience. Everything you know about time might be wrong. You experience time flowing from past to future, But this might be an illusion created by your brain. At the deepest level of reality, time might not exist at all. Einstein's relativity treats time as just another dimension. Past, present, and future all exist simultaneously in what physicists call the block universe. Your entire life is laid out like a path through space-time. You don't move through time. Time is a dimension you extend across. Quantum mechanics reveals something stranger. At the quantum level, events don't happen in definite sequences until observed. Particles exist in superpositions of past and future states simultaneously. The quantum universe exists in a timeless realm until consciousness collapses possibilities into experienced sequences. Some physicists propose that time emerges from quantum entanglement. As quantum systems become entangled, they create correlations that give rise to the arrow of time. The past is the direction of less entanglement. The future is the direction of more entanglement. This might explain what existed before the Big Bang. In a timeless realm, there is no before because there's no temporal sequence. The Big Bang wouldn't represent the beginning of time, but the beginning of temporal experience. The threshold when entanglement became complex enough to create the feeling of time flowing. If time is emergent, then consciousness creates temporal experience. Your brain generates the feeling of time passing by, integrating information from past states and predicting future states. Time isn't something you move through. It's something your consciousness generates moment by moment. Think about where we've journeyed. We explored hidden dimensions beyond perception. We discovered how universe collisions might trigger creation. We saw how eternal inflation spawns infinite realities. And now we've uncovered how consciousness and information might be more fundamental than the physical universe itself. But one mystery remains, perhaps the deepest of all. Why does the universe seem custom-built for observers like us? Part 5. The Universe's Destiny and Deep Mysteries. Dark energy and the impossible force. Something is tearing our universe apart, and nobody knows what it is. In 1998, astronomers discovered that instead of slowing down due to gravity, the expansion of the universe was speeding up. Some invisible force was pushing galaxies apart with ever-increasing strength. Scientists call this mysterious force dark energy, and it makes up about 70% of everything that exists. Yet we can't see it, can't touch it, can't detect it, except through its effects on cosmic expansion. Normal energy gets diluted as space expands. Dark energy does the opposite. It gets stronger as the universe grows larger. The leading explanation involves the cosmological constant, a number Einstein added to his equations nearly a century ago. He called it his greatest blunder. But the discovery of accelerating expansion suggests Einstein's blunder was actually a profound insight. The cosmological constant represents the energy density of empty space itself. Even perfect vacuum contains energy that pushes space apart. But here's the problem. When you calculate how much vacuum energy empty space should contain using quantum mechanics, you get a number that's impossibly wrong. The prediction is off by a factor of 10 to the power of 120. That's the worst prediction in the history of science. If quantum mechanics were right about vacuum energy, our universe should be expanding so violently that atoms couldn't form. Yet somehow the universe has tuned its vacuum energy to a value incredibly close to zero, but not exactly zero. This fine-tuning seems impossible by chance. The multiverse offers one explanation. If infinite universes exist with different vacuum energies, we observe one with the right value because we couldn't exist in universes with the wrong value. But dark energy might also be a leftover echo from the universe's violent birth. During cosmic inflation, Space expanded faster than light. What if inflation never completely ended? What if a tiny remnant still permeates space, providing the gentle push that's accelerating expansion today? Dark energy could be the dying breath of the force that created our universe. The implications for our cosmic future are staggering. If dark energy continues increasing, expansion will accelerate until it tears apart galaxies, solar systems, atoms, and even space-time. This scenario, called the Big Rip, would end our universe when expansion becomes so violent that reality gets shredded. Alternatively, dark energy might fade away, allowing gravity to slow expansion. Or it might oscillate, creating cycles that could lead to future cosmic contractions and new Big Bang events. The fine-tuning mystery. The universe seems designed for our existence, and nobody knows why. You exist because of an incredible cosmic coincidence. The forces that govern reality are balanced so precisely that changing any one by even a tiny amount would make complexity impossible. Consider gravity. If slightly stronger, stars would burn through fuel in millions of years, never giving life time to evolve. If slightly weaker, stars would never form because gas clouds couldn't collapse. The electromagnetic force shows the same precision. Make it stronger and chemistry becomes impossible. Make it weaker and atoms fall apart. The strong nuclear force is tuned even more precisely. Change it by just 5% and you eliminate either carbon or oxygen. Without both, life's chemistry becomes impossible. The odds of all these constants randomly falling within the narrow ranges that allow complexity are essentially zero. This forces uncomfortable questions. Did something set these constants deliberately? Most physicists reject intelligent design but face equally mind-bending alternatives. The anthropic principle suggests the universe must be compatible with conscious observers because we're here to study it. We don't observe random constants because random constants don't produce observers. In an infinite multiverse, observers always find themselves in universes capable of producing observers. But some physicists propose something more radical. What if consciousness plays a role in selecting physical constants through quantum measurement? If observation collapses possibilities into realities, then observation might tune the universe to be compatible with observers. Consciousness and physical reality could co-evolve together. The ultimate fate and information paradox. Everything that ever happened might be recorded forever in reality's fabric. Information about this moment is being encoded into space-time's quantum structure. Every thought, every quantum interaction creates permanent records. Information conservation states that information can never be destroyed, only transformed. When you burn a book, the information gets encoded in smoke particles and radiation. Every event might be preserved forever in reality's quantum information structure. The universe might be a cosmic library containing perfect records of everything that happened or could happen. If information conservation is absolute, then what existed before the Big Bang must still exist in our universe's quantum structure. The pre-Big Bang state was transformed into our spacetime's initial conditions. Future civilizations might develop technologies for reading these cosmic records. If consciousness is information, then conscious experience might persist in spacetime's quantum records. The far future depends on dark energy. If constant, we face heat death. If increasing, we face the Big Rip. If decreasing, we might face the Big Crunch, potentially triggering a new Big Bang. But if consciousness plays a fundamental role in quantum mechanics, then the future might depend on whether observers survive. The strangest possibility involves consciousness actively shaping the universe's destiny through quantum measurement. If observation determines reality, then conscious choices made by future civilizations might retroactively influence the physical constants that allowed consciousness to emerge. The universe might be a self-consistent causal loop. Asking what came before the Big Bang becomes equivalent to asking what consciousness will become in the far future. The mystery might only be solved by conscious beings who survive to time's end and discover their role in creating the beginning. We are the universe becoming aware of itself, participating in the eternal dance between something and nothing, between the questions consciousness asks and the reality it helps create moment by moment. Perhaps this is the quietest yet deepest thought of all, that beginning and end are not separate, that consciousness is not merely a random byproduct of the universe, but part of its very inner fabric. If information is never truly lost, then nothing ever completely disappears, not the past, not the future, perhaps not even ourselves. And so we stand here in this brief moment of cosmic clarity, questioning, wondering, participating, not as spectators, but as expressions of a universe that is beginning to understand itself. And as you know, each night we come one step closer to unraveling the mysterious secrets of the universe. Don't forget to subscribe to the channel and like the video so you don't miss the journey. Thank you.